Just give me a couple of minutes. I'm setting up. Yeah, so in the meanwhile, can you guys share where did you guys feel it is tough? Where did you guys feel it was not good enough explained in the lectures? Or which topic did you find it that you were not able to grasp it? Am I audible? So it means you are able to understand most of the parts. There is one note.
Hello.
Yeah, go ahead, please, Deepak.
Sir, in three-phase transformer where we have to use delta connection and star connection.
Yes, yes. So you felt difficulty in delta star three-phase transformer connections? Are you speaking right now, or is there any network issue, or am I not able to hear properly? He is silent for some reason. Okay, anyway, let us start. I wanted to start with a problem. If we will face any issue in this problem, then we can go back with basic concepts. Where did you guys faced any issue? Okay, so please read this question very carefully. This is a three-phase transformer problem. And after reading, after analyzing the problem, you have to let me know the approach. How should we proceed to the problem? Yeah. Any comment? So see, let me read it for you. Yeah, so 100 MVA, 230 by 115 kVA, basically 2:1 kV, delta star, three-phase transformer, power transformer, has a per unit resistance of 0.015 per unit is given with reactance value of 0.06 per unit. Okay. So it means we are given with per unit resistance and reactance. What does it imply? It implies that we can take either side of resistance and reactance. Can anybody tell me what is the significance of per unit reactance or resistance or impedance?
Sir, your screen is not visible, sir.
Oh, not visible. Thanks for letting me know. I don't know why. So you guys were not able to see the problem?
Sir, at the starting, we had seen it. I have taken a screenshot, sir.
Okay.
I was reading that.
Oh, okay. Please, if any issue occur, please let me know instantly. Okay. And thanks for letting me know. So I was reading this problem. Here we are given the resistances and reactances in per unit, right? So I was asking what is the significance of per unit resistance? What are the benefits of per unit resistance, per unit reactance, or per unit values of impedances?
Sir, per unit values can be used in either side, HV side or LV side without any transformation. And
Exactly, that's what I was looking for. So yeah, and anything you want to add on?
sir, per unit resistance value also gives the copper loss in per unit.
Perfect. Yeah, it is correct. So per unit resistance also gives you rated copper loss value, right? So if we have that knowledge that these parameters or these data are given, now we will proceed with the last statement of the problem statement. The excitation branch elements are also that excitation branch elements are very high compared to your series resistance and reactance. So uh, from that value, you can identify that it will have very less amount of current flowing in the excitation branches for obvious reasons, right? Uh, Now, in the first part, we have to find out or we have to draw the phasor diagram, right? Phasor diagram of one phase of the transformer. So if this transformer supplies a load of 80 MVA at 0.8 power factor lagging, then we have to draw the phasor diagram of any one phase of the transformer. I hope this part is clear.
Yes, sir.
Okay. So the first thing what we will do, okay, we have to compute base value of everything. As
Okay,
soon
sir.
as we encounter any per unit system in the problem, instantly what we should do, and you see in the problem, if data are given in the format of per unit along with actual values, then we have to first thing we need to compute the base values of voltage, current, and impedance. Okay. If everything is given in only per unit, then you do not need to bother to find out the base value and all, because your answer would also be asked in per unit. So you should avoid going into base value or actual value. Okay, so here in the problem, we are given with actual values as well as per unit values. So we should proceed with calculation of base values first, right?
Okay, sir.
So what will be the base value of apparent power?
So the rated apparent power, sir.
Yeah, correct. So base value of kVA would be 100 MVA. Base value of voltage. Let us suppose we have 230 and 115 kV. It is given in the problem, and I am just drawing the notation here. I am not drawing the actual transformer. So if you are considering only this side, okay, let me break it into two parts. If you are considering only left hand side where 230 volts, so base value of the voltage on the left hand side will be 230 volt only. Okay,
Okay.
so V base on the left side is 230 volt, and V base on the right hand side will be 115 kV. Okay, so these are
Yes.
all must be given in RMS. So you might be well aware that all ratings are mentioned in RMS terms. Okay.
Sir,
Now
it is
in the
always
first,
the case.
yeah, it is always the case unless it is stated.
Sir, the nameplate ratings are always in RMS.
Always in RMS.
Okay, sir.
230 volt, 400 volt, everything is written generally in RMS unless it is stated. All the nameplate values are in RMS. Okay,
Okay, sir.
then. So in the first part, it is mentioned that 80 MVA of load, that transformer supplies a load of 80 MVA at 0.8 power factor. Okay, so
Okay.
given load KVA is 80 MVA, right? So
Okay, sir.
we can say that load KVA in per unit, or S is load in per unit, will be how much?
80 by 100,
80 by 100,
0.8.
0.8. Yes, it will be 0.8 per unit. Okay,
Yes,
now
sir.
if it is 0.8 per unit, we are done with apparent power. Now we have to find out the load current in per unit at this load. Okay, so
Okay.
first thing what we will do, we will compute I base. How to compute I base?
Sir, divide, sir, ये KVA base by voltage base.
Yeah, KVA base by voltage base. So here it is MVA, so we will take 100 MVA, 100 into 10 to the power 6. Basically, let me write the expression as well alongside. S base divided by root 3 VL base. Unless it is stated, we will assume it is given in delta or a star. So we are computing line value, or sorry, base current on the secondary side. Why we are computing base current right now on the secondary side? Because that is required, because load is connected on the secondary side.
Okay, sir.
So that's why I am taking the factor of root 3. Why? Because a star is on the secondary side. So I will plug in all the values, root 3 into VL base. VL base is 115 kV. So how much this will come out to be?
I think 502.04.
502.04 ampere is your base current. Okay.
Yes.
Yeah. So, and now we have to find out the load current in per unit. Okay. So if you will compute the load current in per unit, it will be so first we will compute the actual value. Okay, IL actual. So how to compute IL actual, load current of actual?
Sir, the load power divided by the secondary side
Same.
voltage.
Yeah, same thing. Only the change will be in MVA rating or KVA rating. So it is 80 MVA. So 80 into 10 raised to power 6 divided by root 3 into 115 kV. Okay, so this is, it will come out to be, please compute it for me.
Sir, 401.63.
401.63 amps. So if I need to now compute the load current in per unit, it will be 401.63 actual value divided by base value. Base value is 502.04.
04.
Yeah. So how much it will be?
So 0.799.
0.799. So better call it 0.8 per unit.
Okay, sir.
Okay. So now, after doing such a huge and lengthy computation, we could have directly said that load current is 0.8 per unit. How I am making this as a statement, we could have directly called it. Why? Because load kVA is 80 and base kVA is 100. Okay. So, voltage ratings are same. So as load is changing, load kVA is changing, so your per unit of current is, indirectly you can imply that your per unit current is changing, and only change will reflect in per unit. So earlier it was 1 per unit, base value was 1 per unit at rating, and when it comes to 80 MVA, your base or your per unit value of load current is 0.8 pu. Okay. So in any competitive exam, if you face such kind of a statement, you can directly conclude with this statement as IL per unit would be 0.8 per unit, right?
Okay, sir.
Okay. So since now we are done with load current in per unit, and we are given with power factor angle, it is 0.8 power factor lagging. So we can write it as minus 36.86. Since 0.8 and 0.6 power factors are very common, they are very general, very common in machines and power system and power electronics problems. So you should remember this value. Ideally, it will be set up in your mind by now, by the time you will graduate. So it is 36.86 and 53.13 for 0.6. So these two values are very important. Now, moving forward, let me draw an equivalent circuit for this problem for a phase. Okay. So since everything is given, first we will have supply on the primary side. We will have excitation resistance, magnetizing inductance, and this is secondary voltage. This is primary voltage. Okay. This is excitation resistance is 100 pu, 100 pu and 20 pu. And these are 0.015 pu and 0.06 pu. Yeah, you want to say something?
No, no, sir. I got confused with the values of reactance.
Okay. So are they clear now?
Yes, sir.
Okay. Okay. So I hope equivalent circuit is fine for you. Okay.
Okay, sir.
Now, what we will do, we will first compute the base value of impedance. Okay. So Z base. Since we are dealing on the secondary side, right, we are more focused towards the secondary side because load is connected on the secondary side. So we have to take base value from the secondary side as a voltage. Anyway, MVA and KVA ratings are same. So secondary side is connected in a star, right? So if it is connected in a star, we can say that KVA square divided by MVA, right? It is connected in a star. So it will be 115 square divided by how much? 100 MVA. Sorry. So it will come out to be how much it will be?
Sir, 132.25.
132.25 ohm, right? Okay, so we computed base value of current, base value of impedance, right? And in the first part, we were asked with the voltage, we were asked to draw the phasor diagram of any one phase. So
Okay,
for
sir.
phasor diagram, you can see from the equivalent circuit, okay? This is the equivalent circuit. So let us say, let us take secondary voltage as a reference, okay? We will take Vs as equal to 1 angle 0. Okay, fine. Now, next thing we should draw is secondary current. Okay, secondary current is lagging with angle of 36.86. And its value is 0.8 angle minus 36.86. Okay, so this angle also we can write it as 36.86. So to compute the, also to complete the phasor diagram, what is left? We have drawn voltage and current. What is left here?
So the drop in the windings.
Drop in the winding. So basically we are left to draw primary voltage, right? So how much primary voltage will be and how much angle it will lead or lag from the secondary voltage. So to do that, we need to find out the primary voltage. And to find out the primary voltage, we have to apply simple KVL here. Okay. So we can write, can anybody lead me to the equation of KVL in this situation or in this circuit? What should be the equation of primary voltage in terms of this given circuit parameters?
Sir, Vp is equal to Is into Ze plus
Yes,
Vs.
Is into Z plus
E
V, ZE, Z equivalent plus Vs.
plus Vs.
Great. So since we are in per unit system right now, so we can ideally exploit the per unit things. So Is is 0.8 angle minus 36.86 into Z equivalent will be 0.015 plus Z 0.06, right? So this is the one part ISZQ plus VS is one angle 0. Okay, so now it's just that complex calculation. I think you can do it. So please compute it and let me know the value of primary voltage in with magnitude as well as angle. Okay, so these type of calculations are very important for exam purpose. You should be very handy with these calculations. The quicker you will be able to solve these kind of calculations, the more time you will get in your exam.
Sir, it is 1.038 and angle
1.038 at angle
1.72.
1.72. So if this is the answer and if everyone is getting same, if everyone is computing it, so I will consider it as a answer and I will proceed. Okay, so now we have primary voltage magnitude as well as angle, so we can conveniently draw it. It is leading with 1.72 degree. One point zero 38 at an angle 1.7. So this is your complete phasor diagram. Okay. Any doubt in the first part? Anybody?
Sir, for calculating the I base, sir, we have
Yeah,
not used the
we
for the
have not
secondary side.
used the secondary side. Sorry.
Sir, the formula S is equal to root 3 multiplied by VL IL.
Yes.
For the secondary side, we have not used it when we were
For the
calculating the I load
I
per unit.
load. Okay, so see.
Sir, you have said once there is a shortcut. We will use the per unit MVA value and per unit voltage value
Huh,
to calculate the
huh.
load current in per unit.
Yes, yes.
So there we have ignored the factor of root 3, sir.
In which part you are saying exactly? Could you lead me that? In
Sir,
the secondary side, load current per unit value you are saying.
sir, yes, sir. You have said it already. You have not drawn it on that sheet, sir. So
Okay.
when we have calculated by the long method, you told us that
Mhm,
it might be beneficial time
mhm.
saving to use the per unit values to
Yes,
calculate
yes.
the. So
Yeah.
for
So,
calculating that, you told that S is 0.8 per unit and
mhm.
V is 1 per unit.
Huh. So your I will be 0.8 per
Right.
unit.
Yes, sir. Sir, so
Yeah.
here we have
So root three factor we did not consider. That's what you want to say.
yes, sir.
Yeah. So see, root three factors are only in actual ratings or in what to say, whenever you are dealing with actual values, you deal with root 3 factors and all. In per unit system, there is nothing like root 3 or any factors we consider. Why? The reason being is, if you have per unit value, let's suppose you have 0.8 per unit value, okay?
Okay, sir.
And let's suppose you have a delta connected whatever load, okay, delta load. Now in delta load, you have a ratio of line current is equal to root 3 times phase current. Now I have concluded that load current in this delta is 0.8 per unit. Now I want to know the base value, sorry, I want to know the phase value of load current. Okay. So what I will do, I will just multiply this 0.8 into I phase base. Okay. And at the instant I require to compute line current of load current, line value of the load current, I will just multiply 0.8 into I line base. Since base value will change for each thing, either it is phase, it will be some other, it will be line, it will change accordingly. So your per unit will not change. Even for when you compute impedance Z, what do? You change your Z base. How? For a star, it is kVA square by MVA. For delta, what it becomes? Do you have any idea what it becomes?
Yes, I don't remember that.
3 kVA square by MVA. Okay, when you derive this, you will change, these base values will change. So, as per the condition, base value automatically changes. But your per unit value, if your Z per unit is 1, okay, 1 per unit. Now, if you want to compute it for a star, you multiply it with this. If you want to compute it for delta connected load, you multiply with this. Per unit into base value will give you actual value.
Okay,
Did
sir.
you get my point? So there is no factor of root 3 or anything exist in the per unit system.
Okay.
Once you have considered a base value, you have to stick with it. So that's all. Apart from it, any other doubt in this first part?
No, sir.
Okay, great. So if not, then we can proceed with the second part. Could you please lead me how to proceed with the second part?
Sir, one thing came to my mind, sir.
Huh.
Sir, for drawing the phasor diagram,
Yes.
we can assume primary or secondary any voltage as, at 0 degree, sir,
Yes. It's in your hand. Yeah.
according to our convenience.
Yeah, according to your convenience. And when it will be much convenience, when you consider whatever the side of parameters are already provided. Okay, so then it will be convenient because you know that value. Now you know only unknown value. So the known value should be always taken as a reference. In this case, secondary value was given already. So and secondary current was given. So we consider them as a reference as secondary voltage and we led. But anything you can consider as a reference and you can proceed. Is it fine, Neeraj?
Yes, sir.
Okay.
Sir, can we use the per unit values for voltage regulation calculation?
Definitely, and it will be much advantageous if you compute per unit value, if you compute voltage regulation with per unit method. It will be very convenient.
Sir, so then in part B, we have to convert the ISZEQ value into per unit value, then divide it
Y- y-
by base.
yeah. Yes, you are right. So since we have considered, uh, we have already computed primary voltage in per unit, right? So what will be the voltage regulation here? Voltage regulation will be V secondary at no load minus V secondary at full load, right? Divided by V secondary at full load. And V secondary at no load will be equal to V primary. Am I correct? And here we do not need to take care of angles. So you can just consider magnitudes. Now it is crystal clear, I guess. You can easily compute the value.
Hello, sir.
Yes.
Sir, sir,
Yep.
secondary no load value was replaced by primary value, sir.
Yes. You have doubt in that? Yeah, it's
Yes,
good that you have doubt in that. So see this equivalent circuit.
yes, sir.
Okay.
We use this equivalent circuit.
Yeah.
Sir, in the denominator, we have written VS.
Vs. Yes. So basically, no load minus full load divided by full load.
I think it was no load voltage.
Yeah. In some textbooks, it is mentioned that no load in this denominator. But if in many exams they basically follow, if you consider GATE as a standard exam, they always give value based on the full load. And basically, in most of the foreign authors' books, they consider full load on the denominator. But even if you consider no load value on the denominator, it will come close. But why to take risk, right? So
Okay, sir.
full load is considered most of the times.
Sir, while calculating IS into ZEQ, we get 0.0495 with an angle 39.1. So we have to ignore the angle. We will only use the magnitude value 0.0495 in the numerator.
Could you come again, please? Please repeat it.
Sir, the VP minus VS is equal
Yes.
to IS dot ZEQ.
Okay. Yes. So you can only consider this value. Yeah, that's great. You can ignore that angle and you can use this value. So what is the magnitude of ISZ equivalent?
0.0495.
0.0495 divided by 1 angle 0. Sorry, why I'm taking angle. So it should be for
115
115. Oh, no.
kV.
No, it is voltage regulation, right?
Okay, sir.
So it is 0.0495 you told, right? So it should be 4.9% of voltage regulation. Okay.
Okay, sir.
So, uh, okay. So if it is 0.0495, it will be 4.9 percent. But why I am doubting it? Because I
Yes.
can see it in my front that VP we have computed 1.038. So 1.038 minus 1, so 0.038 divided by 1. So it should be 3.8%. So either
Okay, sir.
you might have done some silly mistake in computing ISZ equivalent, but it should be 3.8%.
Okay, sir. I'll try it once more. Or should we move
Yeah,
ahead?
yeah, we should move ahead. You can verify on your own in leisure time. Okay.
Okay, sir.
Okay. So in the next part, a sketch the equivalent circuit referred to the low voltage side of one phase of this transformer. Calculate all the transformer impedances referred to the low voltage side. So low voltage side is the a star connection, right?
Yes,
So
sir.
according to the star side, we have to take a star side as a reference, and we have to refer all the parameters towards the star side. So equivalent circuit we have already drawn in terms of per unit. Now we
Yes.
just need to multiply with its base value, and we can come up with equivalent circuit parameters. So let us proceed.
Okay, sir. Sir, please excuse me for a minute, sir.
Definitely, definitely. Take your time.
Yes, sir.
Yeah. So shall we proceed?
Yes.
Yeah. Uh, so we have already the equivalent circuit here. Okay. So
Yes.
now we want to convert everything in actual value. So that's all our task is for part C. So let us do that. We have already computed the Z base here, 132.25. Now we want to uh, first we will proceed from the right hand side to left hand side. So uh, our secondary reactance would be, let us find out. or secondary equivalent, it is given 0.06. So if it is given 0.06 per unit and you have the base value of 132.25 is your base value, this is your per unit. So how much it will come out to be?
7.935.
7.935 ohm. Okay, so this is your equivalent secondary impedance. Now R2 equivalent is 0.08 per unit into same 132.25. So it will come out to be
0.08.
0.08. No, 0.08 into 132.25. So it should be, sorry,
10.5.
10.5. It is 0.08.
Sir,
What is the
0.015. I think it is.
0.015? Yeah, I did mistake. Sorry for that. So it is 0.015 into 132.25. It will come out to be
1.98.
1.98 ohm. Yeah, it's correct. 1.98 ohm. So we are done with the series parameters. Now coming back to the parallel parameters. So RC is 100 per unit. Okay, 100 per unit into 132.25. So it is 13.225 kilo ohm. Okay, XM is 20 per unit into 132.25. So it will be 0.5 and 32 264, 26.4, 26.45 kilo ohm, I guess. 405.
2.645 kilo.
Oh, okay, 2.645. Okay, so these are all your series, the series impedance and parallel impedance values. Okay, so you just need to plug in this equivalent circuit and you are done with it.
Okay, sir.
Okay, so what is the last part? Last part is a bit interesting. We have to determine the losses in the transformer and the efficiency of the transformer under the conditions of part B. So part B condition is basically part A condition. So when 80 MVA at 0.8 power factor lagging, we have to compute losses in the transformer and efficiency of the transformer. Okay, great. So since we are dealing in terms of efficiency and losses, okay, so first copper loss we can straight away find out. Okay, so first thing we will do, we will find out the copper loss along the series parameters. Okay, so let me take here the space. And what is the better approach? Should we go in per unit or actual value?
Sir, per unit will be easier, sir. It is already given.
Yeah, definitely. So I would also prefer per unit here. So first we will talk about losses, or let me write down the expression of efficiency, P out by P in. Okay, and
Okay.
P out is given or P in is given?
P out is given, sir. 80 MVA.
P out is, yeah, perfect. 0.8 into power factor, right? So 0.8 and power factor is 0.8 also. So P out is given, P in is equal to P out plus losses. So 0.8 into 0.8 plus losses. Now, losses are two kind of, one is core, another is copper. Okay, so first we will find out the losses in our series resistance. So series resistance copper loss would be equal to R2 per unit is equal to copper loss is equal to how much R2?
0.06.
0.0 no 0.015 I guess.
Yes, sir.
R2 per
Yes.
R2 per unit was 0.015. Okay.
Yes, sir.
So will it be the value? Is it correct? That's what I'm asking.
Yes, sir, it is. No, sir. No, sir. No, sir.
Yeah.
Sir, the load current is lower, sir. Then
Yes. That's the catch here. So here we have to multiply with x square or the percentage of load. So x is how much? X is uh, 80,
0.8.
yeah, 80 by 100, so 0.8. So we have to multiply it with 0.8 square, x square, r per unit at rated value. So it will be your copper loss in series resistance.
Yes,
So it will come out to be 15 into 64. Could you please compute it for me?
sir. 9.6 into 10 to the power minus 3.
9.6 into 10 to the power 3.
Minus
Minus
3.
3, right? Minus 3 per unit. Okay. So this is the series losses in the series resistance. Okay. Now another resistance is present in the circuit. That is the excitation resistance or core loss or the magnetizing branch resistance, whatever you can call, or core loss component of resistance. So that loss will be, how to compute that loss, copper loss in parallel branch. How to compute? See this circuit. Okay, let me bring this circuit to you. Now, how much losses will be in this?
Sir, VP square by
Perfect.
R.
VP square by 100 per unit, right?
Yes, sir.
Yeah. Just give me a moment, please.
Okay, sir.
We will do VP square divided by that excitation resistance. So it will be 1.039 square divided by 100. It is 0.0108 per unit. Okay, so we have dealt with all the resistances. Okay,
Okay, sir.
so these are all the losses here. And now, if I will try to find out the efficiency in percentage, we have already output power divided by output power plus losses. So 0.064 divided by 0.064 plus 0.0096 plus 0.0108, okay, into 100%. So whatever the value will come, you calculate that, and that will be the value of your efficiency.
Okay, sir. Sir, it is coming about 96.91%.
96.91%.
Yes, sir.
So that is the value. Yeah, thank you very much for calculating that. So that is all from the first part.
Hello.
Yes, yes. Go ahead, please.
Yes, sir. Sir, this conclusion, this question has finished.
Okay, so no doubt in this problem, right? So let us proceed with another problem. Yeah. So this is again question based on three-phase transformer. Okay, 320 kVA, 24,277 volt distribution transformers are connected in delta star. And here again we have to draw per unit equivalent circuit of the transformer bank, voltage regulation, and efficiency. Similar things, but for different scenario. We are given with short circuit test data and open circuit test data. So we have to apply our test data concepts from the single phase transformer straight away to this problem.
Okay, sir.
Okay.
Yes, sir.
Okay then. So what was the concept there? So let me first draw here equivalent circuit. Okay, equivalent circuit is similar. So from open circuit data, what we can extract?
Core losses.
Core loss, which is already given in this problem. So, but the catch here is phase value is given 277 value, or line value is given 480. So is it root 3 times of 277?
Yes, sir.
Okay, so it is matching. So no need to worry about that. And from the short circuit test, we we ideally compute rated copper loss, and it is given here 912 watt, and we have to identify whether it is rated or not. So 912 watt is at 1.8 ampere, and how can we identify 1.8 ampere is rated or not? So is there any way to find out?
Sir, we have to calculate.
We have to calculate the current, right?
Yes, sir.
Rated current, and we have to match whether it is same or not.
Okay, sir.
Yeah.
320 kVA transformer. Sir, in Y connection, the phase current is equal to the line current, sir.
In Y connection, phase current is equal to line current. Correct.
Yes, sir.
Yeah.
So for one phase is formed by one single transformer. So using that data, when we divide
Mm-hmm.
to 20,000 volt amperes by 277, the secondary side voltage,
Mm-hmm.
the current rating comes out to be 72.2.
Is equal to 72.2.
Sir,
Okay.
why we use root 3 factor, sir?
Root 3 will be there in star, right? KVA is equal to root 3 VL IL, and IL is equal to I phase. IL is equal to I phase, right? Huh. IL is equal to I phase.
Sir, we use root 3 when we have provided with the power of the bank, total bank, sir. Sir, the data is given for a single transformer,
Okay, okay.
320 kVA
Uh,
transformer.
320 kVA. Okay, okay, okay. Yeah, yeah, yeah. Thank you very much. I missed that part. Yeah, yeah. It should be like this. Yeah. Hmm. So if 320 kVA is given, so 72.2 ampere is rated value of the current, and here we are dealing with 1.8 ampere of current. So basically, this loss is not at the rated, it is at some percentage of the load, and that percentage will be how much? That percentage will be this 1.8 divided by 72.2, right? And yeah, so it will be some percentage. Okay, so whatever this value, so from this statement or this calculation, what we figured out is this value is given at certain load. Okay, and this value at that load we are given with, so we do not bother about in calculation of copper loss about rated value. So we know that this loss is not occurring at the rated point. Now core loss is also given, and it is constant loss, right? So now the next part is to uh, first we will go step by step. So first part is find the per unit equivalent circuit of the transformer bank. Okay, so we will compute or we will draw equivalent circuit of the transformer bank. So this will look like again something like earlier what we have drawn. Okay.
Okay, sir.
Okay, now we have to find out the R equivalent, X equivalent, IS, IP in per unit. Okay, so how to proceed for this? We know that we can compute parallel branch parameters. Let me also write excitation. Okay, X excitation. Huh. So parallel branch parameters we can compute from open circuit test, and series parameters we compute from short circuit test. So if we want to compute series parameters, okay, so series parameters, how did we proceed? ZSC, okay, ZSC is equal to V phase SC divided by I phase SC. We have to be careful whether we have to, where we have to consider phase value, where we have to consider the line value. Okay,
Okay,
so
sir.
now so this secondary side is connected in star or delta. It is connected in star.
Star.
Okay, yeah. So in the star, uh, it is connected, but In star it is connected. Okay, fine. Now short circuit test was performed on the high voltage side. Okay, and the following data were recorded. So high voltage side is delta side. Okay, so when it is performed on the high voltage side, so we are referring all the parameters from the high voltage side. So we have to consider accordingly uh, phase value of high voltage side, which is given 1400 volt. Short circuit test data is given 1400 volt of the voltage, and these all parameters. See, one problem we did in single phase transformer similar to this, where parameters were mentioned that it is given on which voltage side, high voltage side or low voltage side, and that voltage side was, in that case of single phase transformer, there was no star delta, but here we have to take care of a star or delta. So here
Okay,
high
sir.
voltage side is delta connected, so we have to figure it out phase value of this line of this voltage, short circuit voltage data, and phase current of this short circuit test data. So phase value of this short circuit test data will be, I phase will be 1.8 divided by root 3, whereas phase voltage of short circuit test data will be similar. Okay, so this will be 1400 divided by how much? 1.039. So it is 1347 ohm. Am I correct till now? Any doubt in this?
Sir, I'm thinking about it, sir.
Okay, take your time, you think about it. So we have computed our series parameters of this resistance and reactance, but indirectly we have computed this impedance. So now the next part is how to proceed to our resistance and reactance. So for that we need that power factor angle, right?
Okay, sir.
So okay, so power factor angle will be, how to compute power factor angle from this short circuit test data? So basically, we are given with the losses, we are given with voltage and current. So now power we know, root 3 VL IL cos theta, and power is given as how much? It is given as 912. Okay, so now we can equate 912 is equal to root 3. VL is 1400. IL is
1.8.
1.8. So now cos theta will be how much? 912 divided by root 3 into 1400. How much is it coming?
Sir, I'm calculating, sir. Please give me
Yeah,
some time.
please, definitely.
Sir. 0.2.
0.2. So how much angle will it be? Cos inverse 0.2.
Inverse of 78.46.
78.46 degree. Okay.
Sir, I have a question, sir.
Please go ahead.
Sir, this ZSC that we have calculated 1347, it is for the whole bank, sir. Sir,
Huh, huh.
sir,
Just
we are drawing.
let me okay, let me confirm it for you. three 20 kVA distribution transformer are connected. So it is for no, it is for this parameter. This is for one phase, right? So it is for one phase only.
Sir, it is said that open circuit test was performed on the low voltage side of this transformer bank, and
Hmm.
short circuit test was performed on the high voltage side of this transformer bank. So when
Yes,
data is given for the bank, then the Z value will be for the uh, bank.
for the bank. Yes, correct. But that is for bank. You are correct there. But when we are drawing equivalent circuit, we are calculating the phase value only, right?
So for phases, we shouldn't we divide it by 3?
Uh, for phase, yeah. So we have considered that factor now here. Here, if you multiply it with root 3, it will be 1.8, right? So that impedance will be whatever come for that value. So we have taken care of that factor. We are taking only phase value of voltage, phase value of current for this
Okay,
three
sir.
phase. Yeah.
Okay, sir.
So we have incorporated all the factors in the solution.
Okay, sir.
Yeah. So this 78.46 degree is the angle here. So now we can compute R and Z. So R is nothing but Z cos theta. So 1347 into 0.2, it should come out to be how much?
269.4.
269.4 ohm, and X is 1347 into cos
Sir,
5.54. Yeah, go ahead, please.
sin theta, sir.
Sin theta, yeah. Oh, sin theta or cos this much. Sin 90 minus cos 90 minus theta is this much. Sin 78.46. So how much is it coming?
1319.77.
1319.77. Oh, okay, so now we can write the series equivalent parameter is equal to, first I would like to write in terms of polar form. So 1347 angle 78.46 degree is equal to 269.4 plus J 1319.77. Okay, so this is all. Now these are very high values, and we already decided that we have to draw, or in the question also it is asked that per unit equivalent circuit we have to draw. So we have computed actual value of this impedance. Now to draw per unit we need base value, right?
Yes,
So
sir.
Z equivalent by Z base, and these all are performed on the high voltage side. So high voltage side was uh, our delta side.
24,000.
24,000. So 20 kVA divided by 24,000. Sorry, 24,000 kVA square by SVA, right? So let
Okay,
me,
sir.
so Z base is equal to kV square by S or MVA. But
Sir, it was 3 kV square, sir,
3
for
kVA
delta.
square. That's what I wanted to check. Yeah. So 3 kVA square here, and it is 3 into kV is 24,000. Sorry, 24. 24 kVA square divided by MV. So MVA is 20 into 3. So 20 into 3 is equal to 60. So basically we have to take 60 here. Why 60 I am taking here?
Sir, 20 kVA is for a single transformer. For the bank, it will be 3 times 20, 60 kVA.
Perfect. Yes. So it is 20 into 3. So this base value will come out to be, please calculate it for me.
I think there is. Sir, here it is given MVA and our power rating is in KV. Sir,
Okay,
KVA
kVA. Okay, kVA. So it should be 60. So
0.06.
0.06. Yeah.
28,800.
28,800 ohm is the base value.
Okay,
Okay,
sir.
so we are done with it. And now to compute this R equivalent plus JX equivalent in per unit, we have to divide it to 69.4 plus J 1319.77 divided by 28,800. So this value will come out, and that values will be series parameters in per unit.
Okay, sir.
Please compute it. Just give me a couple of minutes. I will be back.
Okay, sir. Hello.
Hello, are you able to see my screen?
Yes, sir.
Yeah, so could you please let me know the values?
So 0.0094 plus
0.00009 for that,
yes, sir.
plus
J 0.046.
046. So these are the series parameters that you have computed. So we are done with the series parameters. Now the left out values are parallel parameters. Okay.
Yes, sir.
So parallel parameters we have to compute with open circuit test. All right. So open circuit test data are given, and I think we have to find it out here, RC and XC. So we should go ahead with it. And this open circuit data was performed, open circuit test was performed on the low voltage side of the transformer bank. So low
Yes, sir.
voltage side of the transformer bank is 277 volt, which is connected in a star connection. Okay. So
Okay, sir.
we can calculate accordingly, right? So yeah. So V by I, again, we have to do the same thing. Z excitation is equal to V by I, and V is 480 volt, and it is a star, so it will change to 480 divided by root 3.
It will go to 277.
It divided by 4.1. So what is the value of it? 277,
67.59.
67.59 ohm. Okay, so this is the impedance of parallel parameters. But don't you think it will lead to a bit lengthy computation? We have to distribute it in parallel. So it's better that we compute Y external as 4.1 divided by 480 by root 3. It will come out to be 1 by 67.59 ohm. And it will give you some Siemens. What is the inverse of 67.59?
0.0148.
0.0148 Siemens. Okay. And this Y or admittance, we can write it as conductance minus susceptance, right? It is called as susceptance. So G minus JB. So it will be a straightforward. Now we just find out the angle and we just multiply it with this series parameter. Like we are performing it like it is connected in series, but admittance is considered as a series parameters when two elements are connected in parallel. So how to compute that angle?
So we'll again use the formula
Same
for
thing.
power, real power.
Cos theta is equal to power, which is 945 divided by root 3. V is 480 volt and it is for the star, so 480 by root 3. Sorry, 480 line value, because root 3 VLIR, right? So we can straight away take the line value. Into line current is 4.1. Any doubt in this?
No, sir.
No. So this cos theta will come out, or okay. Please find this cos theta. Then we will find out inverse of this angle.
Zero 0.832.
0.832. Okay, so Okay, so now if we have this theta angle,
Angle is 33.686.
33.686.
Also.
Now the real part will be 0.0148 into z is equal to 0.0148 into 0.0832, and b will be equal to 0.0148 into sine 33.6. How much g and b values are?
So I'm calculating, sir.
Yeah, please.
So G is about 0.0123 and B is
0.01. B is
0.0082.
0.0082. Okay, on minus k. So these are actual values, right? So now we need to convert it into per unit. So for that, base value is required. So base value is voltage base square divided by S base. Okay, voltage base. Yeah.
So the base value for admittance and impedance will be same, sir.
Okay. So no, it will not be same, but we can inverse it. Once we compute Z base, we just need to inverse it.
Okay, sir.
All other way around is Y base is S base divided by V base square. Okay. Now it will be straightforward. S base is given for this. We are computing on the delta side, right?
No, so star side.
We are computing it on the star side. So star side is this voltage is given.
So this is the wrong
Sorry.
question, sir.
This is
Hello.
480 volt. Yeah, go ahead, please.
Sir, we are doing first problem.
No, we are doing second problem.
Okay, sir.
So our voltage is 480 volt, and it is on the star side. So phase value will be 480 by root 3, and for one phase kVA is 20 kVA, right? So we can do that 20 kVA. So 20 kVA divided by 480 divided by root 3 square, and how much it will come out to be, and after that we will multiply.
$72.2.
72.2 Siemens. So 72.2 Siemens we have to multiply with Z and B. So G into 72.2 and B into 72.2. So, sorry. Divide, right? Not multiply. Oh, these are all Siemens. We have to divide.
To get the per unit values.
Exactly, yeah.
So G per unit is 1.7 into 10 to the power minus 4, and B per unit is 1.1357 into 10 to the power minus 4.
Okay, thank you for calculating. So we are done with parallel parameters as well, right? So we have computed it as this conductance and susceptance. So if you convert or inverse, you will get the resistance or reactance. Otherwise, if it is a subjective question, you can leave it as a conductance and susceptance. Okay, so I think first part is done. Now the B part is to compute the voltage regulation of this transformer bank at the rated load and 0.9 power factor lagging. Okay, so again, we know that voltage regulation, how to compute. We just need to write V secondary at no load minus V secondary at full load. Yeah, so V secondary at no load will be V primary, okay, and for that we need to compute V primary voltage, as earlier we have done that. So V primary is equal to V secondary plus I into Z, I series into Z series equivalent, okay. So V secondary, we will consider it as 1 angle 0, okay. We are taking this secondary voltage as a reference, okay, V secondary, and I secondary will be lagging with some angle, and V primary, we are assuming that it will come out to be leading with V secondary. Okay, so have you computed secondary current, this IS?
I think not.
Not. Then we should calculate it. If not, IS is not computed, yes. At the rated load, okay, so it is very important to find at the rated load, because whatever we did in the first part, that was for given load. So okay, so if we are dealing with per unit thing, I don't think we need to compute. Am I right?
Yes.
So since rated is written, so we can directly consider it as 1 per unit. Where is it? 1. So we can take it as 1 per unit. So I is 1, angle will be cos inverse 0.9.
0.9.
Cos inverse 0.9, and that will be minus because it is lagging, okay, into ZS equivalent. So ZS equivalent we have already computed in per unit. How much it is? It is
Sir, this equivalent circuit of the primary side.
no, this equivalent circuit is for overall a phase of a transformer, right? You can see this equivalent circuit.
Yes, sir. Sir, this is primary side or secondary side?
This is both the sides are incorporated in this equivalent circuit. This is per unit circuit or equivalent circuit. But if we are talking about per unit, we just plug in all the per unit values of parameters, and this is the primary voltage here, and this is the secondary voltage. This is the
Yes,
equivalent
sir.
circuit. This is the equivalent circuit of a phase of a three-phase transformer.
Yes, sir.
So ZS we have calculated already series parameters. It is 0.094 plus J 0.046. Okay, so 0094 plus 0094 plus J 0.046. Okay. So now you have to compute this polar equation or complex equation. So you will get some magnitude as well as angle. So it's better you compute both. However, in voltage regulation, if you are asked in any competitive exam, you just proceed with only magnitude. You do not bother with angle. But since it is a long question, you might need that value of angle in near future. So it's better that you compute it at this stage. Are you getting it, Deepak?
Yes, a little bit because sir, I have skipped due to my laptop is.
Okay, so please revisit the recording lecture of this session. Okay, then it will be clear.
Yes,
So
sir, sure.
I think today we will be completing two long problems on three-phase transformer. So it will give you better idea of three-phase transformer. So Neeraj, are you done with the values?
Sir, I'm doing it, sir.
Okay, okay. And who is this meeting guest? Could you please unmute yourself and let me know whether are you getting these things or not?
Sir, I think it is your ID, sir.
My ID? No,
Yes, sir.
meeting guest is not my ID. Okay, anyway.
Sir, it is 0.989
0.989,
with angle 2.635 degree.
2.635 degree.
Yes.
It is the primary voltage. Then it will come in negative, no? Okay, anyway, but it should not come in negative. But
Sorry, sir. Sorry, sir. I think I have missed the sign for sir. It is lagging power factor, no, sir.
okay, okay. It happens. Do not worry. But it's when it is coming in negative, then be cautious that you might have done some mistake. So this is another way to identify your silly mistakes, and then you can avoid it.
So now the answer is 0.0469.
0.0469.
Yes, sir.
Oh,
With
it
angle
is
52.61.
0.0469 with angle 46.61.
61. So it is the value of IS into ZEQ, sir.
Okay, it is the value of IS into Z equivalent. Okay, so maybe we might have done some mistake in calculation in between. It should not come less than 1 primary voltage. As obvious, you can see that it is an inductive load and resistive on the secondary side. So whatever the primary voltage, that should be higher than the secondary. But anyway, it happens in long problem, in such a long problem. We
Sir, I
do
have
some.
not added, sir, the 1 angle 0, sir. I have
Oh,
told this value to check, sir. If
okay, okay,
it
okay.
is correct,
So,
then I'll proceed.
okay, +1 angle 0, right? So it will come certain other thing. Since I do not have value for this one, so I cannot verify. But anyway,
Sir,
it
after
will
adding, it comes out to be 1.029 with angle
0.29,
with angle 2.077 degree.
2.07. It is looking to be correct. Okay, so now we can compute voltage regulation, which will be 1.029, and no need of including angle, -1 divided by 1, so it will be 0.029, so 2.9% of voltage regulation. Okay, so this is the value of the voltage regulation. The last part is the what is the transformer bank's efficiency under these conditions. So what will be the efficiency? So again, we are given with everything, right?
Yes,
So
sir.
from the series parameters, we can compute from series resistance only. We can compute core loss. From the series, sorry, from parallel resistance, we can compute the core loss. From the series resistance, we can compute copper loss. Okay, and
Okay, sir.
we can compute output power or input power. What can we compute? We can compute output power because we are given in the part B power factor and rated load. So rated load means secondary side current, which is 1 per unit. So and secondary side voltage is also 1 per unit. So let me write output power as Vs Is cos theta. Vs is 1 per unit, Is is 1 per unit, cos theta is 0.9, so it is 0.9 per unit. Now efficiency is P output divided by P output plus losses. So it is 0.9 divided by 0.9 plus P iron loss plus P copper loss. Okay, so iron loss first let us compute. So Vp square divided by R external R excitation per unit. So Vp we have computed as 1.029 square divided by this RC per unit. RC per unit will be or multiply it with G per unit, GC per unit. So 1.7 into 10 raised to power minus 4. Okay, so 1.7 into 10 raised to power minus 4. Why are we multiplying? Because we have computed the conductance value, so we can multiply. We are doing Vp square into G. Okay.
Okay, sir.
So this will lead to some value that will be the iron loss. In the meanwhile, you compute. I am writing the expression of copper loss. So that is Is square R. I is 1 square into R we have computed. So R is Oh,
So
sorry.
G is conductance.
G is conductance here. Yeah. Arc per unit is 0.0094. It is 0.0094 per unit. Okay, so now we can plug in here. How much is the per unit of iron loss?
Sir, 1.8 into 10 to the power minus 4.
1.8 into 10 to the power minus 4. So you compute it, then you will get the value of efficiency.
Sir, in per unit system formula will change.
We change what?
Sir, formula has changed like copper loss or iron loss.
No, formulas are same. That copper loss is series resistance in per unit, right? And core loss
Sir,
is primary voltage square divided by parallel resistance. That is the core loss component resistance, right? If you
yes,
can,
sir.
if you can see here, this equivalent circuit here, whatever loss occur at this, sorry, how much loss occur across this resistance, that will be core loss, and the loss or the value of this resistance, that will be copper loss. So that's what we are writing here. We just need those values.
So the efficiency is 98.9%.
98.9%. So it seems decent value. So this is the answer of the efficiency. Okay, so we have put a lot of effort. Actually, Neeraj has put a lot of effort in calculation, and he has also applied so much concept from the single phase concept, because we had the background of single phase transformer voltage regulation efficiency calculation, and we had to apply those background concepts in the three phase transformer. But we have to take care of phase and line values separately. And also we have discussed that per unit values doesn't get affected with the factor of line or phase, or with the factor of √3. So that's the advantage of per unit system. Since when you are dealing in per unit system, it gives you the freedom to avoid all the factor or ignore all the factor, and you just proceed with the rated value. Okay, so that's the advantage of per unit. And whenever you get the chance to solve such problems, such a lengthy problems, see, both the problems were so much lengthy, both of them took complete 2 hours almost. So when such question comes in exam, you do not have 1 hour to solve one problem. Or even if suppose you have 4 parts and you are solving in 1 hour, it means one part is taking you 25 minutes. So you cannot spend so much time in the exam. So straight away, if you are calculated, if basically in exam you will be asked only one part. So when you are asked to compute efficiency, you just proceed with per unit figure. Okay, it will give you very much flexibility, and you will be done in a minute or two. And when you are asked to compute voltage regulation, you do not bother about angles. So try to compute in terms of magnitude as much as possible. Avoid angles when you are asked to compute voltage regulation. Okay. Similarly, when you are asked to find out the rated current, or rated current involvement is there in any part of problem, just see how much is the load MVA ratio from the rated MVA or rated apparent power. So straight away you can derive that value of the power current in terms of per unit, and it will lead you to the fast calculation. So a machine is the subject where heavy and long calculations are required, but with certain tips and techniques, you can avoid those lengthy calculations. Okay, so I hope you must have got idea where to save our time, where to how to do efficient calculation. So just like efficiency in transformer, efficiency in calculation also helps us to execute the problem in very less time. So be efficient in solving any problem. And I hope if there any doubt in these both problems, I would be happy to take that. And at the end, I will leave you with a problem, okay, so that you go and you apply all those concepts you have learned. So this is again a very lengthy problem. It has 5 parts. So I will pose this for you. You solve it. If you face any difficulty, we can discuss it in the next session. But I don't think you will find any difficulty in solving this problem, since we have discussed above 2 problems very in detail. So that's all from my side. Yeah, if you have to say something, please say, and we can wind up the session.
Well, in per unit value is the actual divided by base value, right?
Yes, yes, yes.
Sir, please explain little bit about this per unit system.
See, I have explained in the lecture. You just revisit the recording, okay? You will find there. I have explained what is difference between per unit and actual system, and where to consider what factor. In delta connected load, we have to consider 3 into voltage square divided by apparent power. In a star connection, we have to consider straight away voltage square divided by apparent power. Okay, so we can schedule one detailed lecture on per unit if you guys insist. Then we can explain, or we can derive all the parameters from very basic ones. But I think you will get enough idea to solve transformer problems at least from today's lecture, I guess. Am I right, Neeraj?
Yes, sir.
Is it sufficient for the transformer problem solving, whatever I have delivered today?
Yes, sir.
Okay. So Deepak, you just revisit this recording of today's session. I will upload it as soon as possible, and you solve both the problems on your own. And if you face any difficulty, we can take up in the next lecture. Or you have my
Yes,
mail,
sir.
as you have my mail ID and my number, so you can ask there. Okay.
Yes, sir.
Okay. So thank you very much. Try this problem on your own, and we will meet up in the next session.
Yes, sir. Thank you, sir.
Okay, sir.
Thank you.
Good
Thank
night, sir.
you. Good night. Good night. Good night, Neeraj. Good night, everyone. I am ending this.